In the previous lecture, we obtained the expression of current gain and overall current gain. We also discussed two different cases in current gain, and in this presentation we will find out voltage gain and overall voltage gain. Voltage gain is defined as the ratio of output voltage to the input voltage. The voltage gain is defined as the ratio of output voltage to the input voltage. The voltage gain is represented by A subscript V, and we will first find out the output voltage. The output voltage is equal to minus of input voltage multiplied with the load resistance. The output voltage is the voltage across the load resistance, and if you see the direction of current through the load resistance, it will be like this from bottom to up. This is the direction of output current, and when we apply Kirchhoff's voltage law in this loop, we have minus of IO RL, then we have minus of VO equal to 0. So the output voltage is equal to minus IO multiplied with RL from this equation. IO, the output current, we have already calculated in the last lecture. By using the current divider rule, we can easily find out the output current. The output current is equal to IC, the overall current or the total current, and then we have to multiply the total current with the other resistance. The other resistance is RO parallel RC, because we are having two resistances connected in parallel, divided by the sum of two resistances. So RO parallel RC plus RL. IC is equal to beta times IB, so we have the output voltage equal to minus beta IB inside the bracket RO parallel RC divided by RO parallel RC plus RL, and then we have to multiply it with the load resistance. So this is the expression of the output voltage. Now we will find out input voltage. The input voltage is equal to the drop across the resistance RB or the resistance beta plus 1 RE. The drop will remain same across the two resistors because they are connected in parallel, and we can easily find out the input voltage if we can calculate the drop across resistance RB or drop across beta plus 1 RE. We do not have the value of current through resistance RB, and to find out drop across RB, we have to perform the extra calculation to find out current through this resistance. But we already know the current through resistance beta plus 1 RE, it is IB, the base current. So VI is equal to IB multiplied with beta plus 1 RE. So the input voltage is simply the drop across resistance beta plus 1 RE. VI is equal to IB multiplied with beta plus 1 RE, and to calculate the voltage gain we need to divide the two expressions. So we will divide them, and the result is equal to the voltage gain. Base current IB will cancel out, and the final expression is equal to minus beta RO parallel RC parallel the load resistance. You can see RO parallel RC is multiplied with resistance RL, and then in denominator we have RO parallel RC plus RL, and we already know R1 R2 divided by R1 plus R2 is equal to R1 parallel R2. R1 is RO parallel RC in this case, and R2 is the load resistance. So they are connected in parallel, divided by beta plus 1 RE. So this is the final expression of the voltage gain, and now we will perform few simplifications. In the first simplification, we will neglect beta from the expression because beta is a large quantity and beta plus 1 is nearly equal to beta. For example, let's say beta is 150, so beta plus 1 is equal to 151. 150 and 151 are nearly same, so we can have beta plus 1 equal to beta. So the voltage gain is equal to minus beta RO parallel RC parallel RL divided by beta times RE. This beta and this beta will cancel out, so the voltage gain is equal to minus RO parallel RC parallel the load resistance divided by resistance RE. So this is the expression when we consider beta plus 1 nearly same as beta. In the second simplification, we will consider the fact that resistance RO is very large, and if resistance RO is greater than or equal to 10 times the resistance RC, we can neglect RO. So the voltage gain is equal to minus RC parallel RL divided by RE. In the third simplification, let's say there is no load resistance. This means load resistance is open circuited and it is equal to infinity, and definitely it is larger than resistance RC. It is much larger than resistance RC, so we can neglect the load resistance, and the voltage gain is equal to minus RC divided by dynamic ammeter resistance RE. So this is the expression in the third case, and in many books you will find this expression. You can also use this expression depending on the question, and this expression is the basic expression in which we have considered all the resistances, and we also have beta and beta plus 1 in this equation. So this is the basic equation, and when we perform the simplifications we have different equations for the voltage gain. Now we will move to the next part of this lecture, in which we will find out the overall voltage gain. The overall voltage gain, it is represented by A subscript Vs, and it is equal to the ratio of output voltage to the source voltage. AVs is equal to VO by Vs. AVs is equal to voltage gain inside the bracket input impedance divided by input impedance plus the source resistance. So this is the expression of overall voltage gain, and if you don't know how we have obtained this result, then watch H parameters lecture. In that lecture I have explained how to obtain the overall voltage gain. Now we will talk about the negative sign in the expression of voltage gain. This negative sign represents 180-degree phase shift between the output voltage and the input voltage. So if this is the input voltage and we feed this input voltage to the amplifier, then after the amplification the output voltage, the amplified output voltage, will have 180-degree phase shift. You can see there is 180-degree phase shift between the input voltage and the output voltage after the amplification. So this negative sign represents there is 180-degree phase shift. In order to calculate all these parameters, we must know the value of resistance Re. Resistance Re is equal to 26 millivolts divided by the ammeter current IE. So to obtain resistance Re, we need to calculate the ammeter current IE from the DC equivalent circuit. So every time we will first calculate the ammeter current IE from the DC equivalent circuit, then we will proceed to the AC analysis. This will be more clear when we solve one numerical problem. So in the next lecture we will solve one numerical problem based on RE model. So see you in the next one.